Okay, having a look at 11 maths methods, quiz that we did last week in class, just going through the solutions for that. We're focusing on logs and derivatives in this one, so looking at some simplifying logs. There's no base written, so that's assuming that it is base 10. So we are using our log laws to simplify that. So if we're adding logs, that means we are multiplying the 10 and the 2 there, and then we will divide by 4. So we can make that log 10 times 2 is 20, divided by 4 is 5, and we can simplify it as that. We're not asked to evaluate it, so we're just leaving it in that form. For the next one, we've got this 2 here, and if we're wanting to simplify and bring together as one log, we really need to make that into the form of a log. So we know if we've got our base 10, to get a 1, we would have had log 10, 10. We've got the 2, so we would have had our 2 out the front, and we can bring that up the top and make it 10 squared. So that would give us a 2. And then we've got the log 50 and the log 9. So we can then bring that, so 10 squared is 100. So we can bring that together and have the 100 divided by the 50. But we've also got a plus 9, so we can have the times 9 there as well. So the 100 divided by 50 is going to be 2. 2 times 9 would give us log of 18. Then we've got one where we have some coefficients in front, so we're going to take them up to the top first. So we'll make that log 3 cubed plus log 6 minus log 9 squared plus log 3. So now we're going to bring together all the pluses and multiply those. So 3 cubed is 27. We're going to multiply that by 6. And we're going to multiply that by 3, and on the bottom we have the 81. So then we want to simplify that. So we can either bring that all together on the top first. So we can do the 27 times the 6 times the 3. And get the 486 divided by 81, and then get a 6 there. Or we could do the 20, do a bit of simplifying where we do 27 divided by 9, 81 divided by 9, and simplify that way. These are generally tech free, so you probably would want to go to that. Overall, you're going to get the log 6. Then we've got ones here where we're solving. So if we've got log of something is equal to log of something else, and we've just got the one log there on each side, we're then able to say that the x plus 7 must equal 13, then we're able to say the x must be equal to 13 take 7 is 6. So we're able to get an answer for the x value there. Here we have to do a little bit of work before we get to it. So we have to take that 4 up the top. So log x to the power of 4 minus log x is equal to log 64. Then we can bring that together. Because it's the minus, we will divide. So x to the 4 over x. Now, that means that this part must be equal to that part. X to the 4 over x is just going to give us x to the power of 3. That's equal to 64. And we know that 4 to the power of 3 is equal to 64. So that means x must be equal to 4. On the second side of the sheet, we had some questions relating to the derivative and rate of change. So the first one was finding the average rate of change between 1 and 3. So assuming that means between x equals 1 and 3. So we've got our y equals x squared minus 3x plus 5. So we're wanting to find y1 and y3. So when x is equal to 1, 1 squared is 1, minus 3 is negative 2, plus 5 is going to be 3. And then we've got, if it's 3, we've got 3 squared is 9, take away 9, plus 5 is 5. So then when we're doing our average rate of change, it's going to be our change in y over change in x, or you might write that as y2 minus y1 over x2 minus x1. So we've got 5 take away 3 over 3 take away 1. So we get 5 take 3 is 2 on 2 is equal to 1. Then the next one is wanting you to use find the derivative using first principles. So we've got our y dash is going to be the limit as h approaches 0 for our f of x plus h minus f of x. I probably should have written over here f of x, f dash of x instead, and kept the same notation over h. And then we want to carry this limit as h approaches 0 all the way down the page while we're putting that in. Now, when we're doing the f of x plus h, we're putting in to this one up here the x plus h instead of the x. So we want to put in up here, and I'm going to do that over to the side. When we have f of x plus h, it's going to be, instead of x squared, we will have x plus h all squared. Instead of minus 3x, we're going to have minus 3 outside of x plus h, and then plus 5. So we end up with, over here we would have x squared plus 2xh plus h squared minus 3x minus 3h plus 5. So that's what we're going to put in for the f of x plus h. The f of x is just going to be that part there. So we're going to have our x squared plus 2xh plus h squared minus 3x minus 3h plus 5. And then we're going to subtract the x squared. I could put it in brackets, but I'm going to do it in one step. So I'm subtracting the x squared, I'm subtracting a minus 3x, so that's the same as plus 3x, and I'm subtracting the 5, and that will be all over h. So now I want to simplify what's on top. So I can cancel out the x squared and the x squared there. I can cancel out the minus 3x plus 5 minus 5. So I'm left with 2xh plus h squared minus 3h over h. So this is the step where I now want to factorize and take a h out the front. So I get h outside of 2x plus h minus 3 over h. I can cancel that h out. So then I've got the limit as h approaches 0 of 2x plus h minus 3. Now, I know as h approaches 0 that this will approach 2x minus 3. For part C, it's asking you to do that using the rule. So if we've got x squared minus 3x plus 5, x squared, the derivative of that is going to be 2x. Of the minus 3x, the derivative is going to be minus 3, and the 5 will become 0. So our derivative is y dash equals 2x minus 3, which is the same as what we got in our previous question. Now the last one had sketching the derivative and determining where the gradient is positive. So I'm going to grab my graphics calculator and I'm going to pop that function in there. So I'm going to put my y equals x squared minus 3x plus 5. I'm going to graph that, and there's my function there. When I'm talking about where the gradient is positive, I want to see, we're talking about that line. As we're coming down here, our gradient is negative, and then we stop, and then we go back up. So here's our stationary point. We haven't got onto that yet in class, that part of the content, but we do know that a turning point is a stationary point. We know that the gradient is 0 at that point. So we've got a negative gradient here and a positive gradient here. So I want to know where that turning point is. So I've got my trace on. I think I'm just going the wrong way with it. Here it comes. And I've got that is at about 1.6. To find that actual value, I would say if my derivative is 2x minus 3, I want to find when that's equal to 0. So I would take the 3 over and get 2x. Therefore, my x is equal to 1.5. So I know that it's 0 at 1.5, and I know when x is greater than 0, or greater than 1.5, that the gradient is positive for that section of the graph. So on this side, it's positive. On the other side, it's negative. So when x is greater than 1.5, the gradient is going to be positive.